Put the title slide on the screen primarily for me, not necessarily for you, because it reminds me that I do have indeed the right to upload it. I am what I refer to as an extinguished professor. I have been extinguished since about 2000, and I have an appointment in 3 colleges. College of Science, my home in chemistry, College of Education in Curriculum and Instruction, and I also helped build the School of Engineering Education in the College of Engineering. And we'll take a look at some of the implications of that as we go along. I want to start today by noting that in 1984, we were celebrating the 3rd anniversary of the creation of the first graduate program in chemical education. And so my colleague Dudley Heron and I wrote a paper for the Journal of College Science Teaching, basically describing what it is that we had done and what our hopes were for the future. And then 25 years after that particular paper appeared, one of my ex-students was the editor of the Journal of College Science Teaching. And in spite of that, she was willing to accept a paper that Marcy Towns and I put together, basically looking at the 25 years since the first paper, what have we actually accomplished? I'm going to build a metaphor for my talk today based on some work that was done by the grandson of a dear friend of mine from the University of Illinois, John Baylor. So Baylor and Gornick basically published a paper in the New England Journal of Medicine in 1997. And let's take a look at what it is that they did in this. They attempted to measure progress against cancer. And they chose to measure it by looking at mortality rates from 1950 to 1994 during the so-called war on cancer. And they argued that mortality rates were the best place to get started because it was the most basic measure of progress against cancer, and also, as they said, because it is the outcome that is most reliably reported. Well, when they looked at their data, they came to an interesting conclusion. And they said basically that 35 years of intense effort had to be judged as a qualified failure. And I found that an interesting phenomenon because I knew about the NIH program that had funded this work, and I knew about the other projects that were going on. And I'll give you an assertion, and my assertion is a very simple one, and that is fundamentally different conclusions would have been reached if Baylor and Gornick had examined other forms of progress, such as changes in the length of survival after the diagnosis or changes in the quality of life. And if you'll accept that, then you'll understand my assertion that the choice of methodology can have an enormous effect on the conclusions that are reached in the study. In 2004, I had the opportunity to publish a paper in the Journal of Chemical Education that described what had happened in my life in the 20 years since I first started working with graduate students about what it is that I've learned about doing educational research. And in this paper, I basically argued that there are 3 fundamental elements of good educational research design. The first one is fairly obvious. It's a set of guiding research questions that the study is going to try to answer. So I'll give you a couple of examples of things that we've been working on. One that I'll come back to is the basic idea, how do students who are blind, and have been blind since birth, visualize things such as the 3-dimensional structure of a molecule? Some work that Alejandra Mangana did with Sean Brophy and myself in engineering education, basically asked the question, what are engineering students' perceptions and experiences when exposed to computational simulations? These are not computer simulations, which we have defined as things that you write for use by a student but you would never use yourself. These are computational simulations. These software that was written for use by advanced graduate students, faculty, and practicing engineers that someone then said, I wonder what would happen if we put it into the classroom. There are a couple of related words that you probably don't really need to know, but I'm going to tell you anyways. They're called enculturation and acculturation. Enculturation is something that you have done to children, if you've had children. It is an attempt to bring them into a social structure, oftentimes forced. And you will understand that if you've had children. Acculturation is a very different process. Acculturation is a voluntary process. And the research question we asked here was based on some of our early observations about graduate students who were working in a research group that did organic synthesis. And what we found was that there was very little overlap between what it is that graduate students did when they designed organic syntheses and what practicing organic chemists did. And so we asked, what can we do to help students through the acculturation process to joining the community of practice of real chemists? Other elements of the good research design, I argue, were simply easy to understand. We've argued that a theoretical framework that's consistent with the research questions upon which the study will be built is a fundamental part of good design. Evidence that we're not alone in this can be found by going back a little bit more than 10 years to 2005, when the editor of the Journal of Engineering Education basically wrote an editorial saying that they were never going to publish the kind of papers that they have been publishing for 90 years, that the only things that they would publish were engineering education research, and they would not be published unless it was based on a strong theoretical framework. The third element is a simple one, and that is choice of methodology. And the choice of methodology is basically one that should be consistent with the research questions that you're trying to ask and the theoretical framework that you are using for that particular study. I remember more years ago than I wish to remind people of, roughly maybe 1980, thereabouts, that I went to my first meeting of the National Association for Research and Science Teaching, NARST. And I encountered virulent discussions, not quite to the level of blood rolling down the aisle, but close enough, between adherence of quantitative versus qualitative methodology. I'm not going to get into that debate very deeply, but I will talk a little bit about it. I'm going to try to give you a couple of assertions that we have created about theoretical perspectives, theoretical frameworks. I tell graduate students that what they need to do is choose a theoretical perspective that is best suited to the particular study that they're doing. Indeed, when I have students in the College of Education taking preliminary exams, the exam question I oftentimes ask them is, what theoretical framework are you using for your study? Why did you choose it? What other frameworks did you examine? And why are they not appropriate? I want to point out to you that there really is nothing wrong with having more than one theoretical perspective. We have found that sometimes bringing two into a study helps us increase the sophistication of the results that we get. And this is okay, I believe, so long as these two frameworks at least are not incompatible. One of the things that I've had to tell graduate students all the time is a very simple idea. when you look at the literature, there are many people who have written about a particular theoretical framework. There are many assumptions that people have brought to that particular theoretical framework. And you as a researcher do not have to accept all of the stuff that has been reported in the literature. You don't have to accept all the assumptions. You don't have to accept all of the language if it's not appropriate to a particular study. But I said to them, what is fundamentally important is that you be explicit about which assumptions from that theoretical framework you are actually going to use for a given study, which ones you're not, and why you've made that choice. I want to talk a little bit about research questions, and I'm going to use an example based on one particular piece of work done in my group. The argument I'm going to make is that research questions can evolve. There should be no revolution. People get shot during revolutions. But to the best of my knowledge, no one has yet been shot during evolution. Let me give you an example of this, and I'm going to cite some work that was done by David Gardner, who looked at the learning of quantum mechanics by undergraduate chemistry majors, by graduate students in chemistry taking quantum mechanics courses, and undergraduate students in physics. And when David started his work, he had a research question that he proposed for the pilot study stage, and that is, how do students learn quantum mechanics? And I told Dave, I don't think this is really going to work, but try it. And so 2 weeks after he began collecting data, he came back to me and he says, I have an unambiguous answer to this question, and the answer is not very well. So what we did is we went back and we refined our research questions. What are the experiences that students have while learning quantum mechanics? What are the conceptual difficulties that students encounter? And are the conceptual difficulties the source of the absence of progress in learning? And the third one turned out to be the most useful for us, and that is, how do students approach the learning of quantum mechanics? Well, I started doing research in 1965, and I was an undergraduate. I was a sophomore, and I started to work in a group that did synthetic chemistry. And I soon learned that I am not a synthetic chemist. I therefore decided to become a spectroscopist. My early area of research is Fourier transform nuclear magnetic resonance spectroscopy. I helped build the fourth FTNMR in the US, and we applied it to understanding the structure, bonding of a variety of compounds such as the one that you see here. That spectrum actually has now appeared in a number of inorganic textbooks, and the only reason for that is it's so damn simple, and I labeled the peaks. I've come up with a conclusion based on 50 years of experience as a synthetic chemist, a spectroscopist, and then as someone working with graduate students to do educational research. And it's a very simple one. And that is that the quality of the insight obtained in a particular experiment, or in our case, in a study, is proportional to the difficulty of actually doing the study. It has been 35 years, I believe, since the last time we administered a Likert scale. I'm also going to cite a quotation from one of the first people to write extensively on the constructivist theory of knowledge, Ernst von Glasersfeld, and it's an important one, I believe. Objectivity is a myth that you can make an observation in the absence of an observer. The argument that we will make is that you can try to be objective, but we are humans, in some case humanoids. I would like to give you some assertions about quantitative methodology. I'm going to argue that there is nothing inherently wrong with quantitative research. Last year I was asked to write a book chapter that looked at the evolution of the research that we have been doing for 30 years now. on problem solving in chemistry in various domains. And I pointed out that we started, like so many others who would come out of chemistry, with doing statistical work. The trouble that we ran into is that although we had statistically significant results, we couldn't understand where the results came from. And so we've also concluded that if there's nothing inherently wrong with quantitative research, there is nothing that is intrinsically right about it either. And I will point out that it's been 30 years since any one of the 70 grad students who have worked with me have done anything that is quantitative. So let's take a look at some of the kinds of ideas that have been proposed by Michael Quinn Patton. This is the cover of his third edition. It's qualitative research and evaluation methods. And he defines quantitative research quite easily. He says quantitative methods are succinct. They are parsimonious. They are easily aggregated for analysis. Let me assure you that writing quantitative papers was a hell of a lot easier than writing up the qualitative research. He said quantitative data are systematic, standardized, easily presented in a short space. But I would like to take you back to a quote that was originated by A.E. Hausman. You may have heard a slightly different version of it, but Hausman was the first one to use it. Hausman was a professor at what people call Oxbridge, and they can't remember whether it was Oxford or Cambridge. He was a famous poet of his time, and he has been described as perhaps the best scholar that has ever written about the classics. And he described an individual's research once with the following quote. He uses statistics like a drunk uses lampposts, more for support than illumination. So let's take a look at assertions about qualitative research. By the way, I found this particular image and put it there because I couldn't do that once. And if I tried, I would break. But anyways, what do we know about qualitative research? People say it sacrifices objectivity that results from rigid statistical research designs for a combination of three things that we've come to value: flexibility, particularly depth. We're able to get deeper into the data set, and an extraordinary greater detail. Qualitative research, is done by individuals with a preference for what we'll call hypothesis-generating research. People call it grounded theory, rather than hypothesis-testing research. We've done a lot of work where we were the first people in the area, and we didn't have a hypothesis to test. I'm going to give you an assertion, and that is an argument I'm going to give you that you probably will never hear from anyone else in the world. People who teach educational research methods courses tell you that qualitative data are not generalizable. I think they're wrong. I believe it is quantitative data that is not generalizable. Quantitative data can't be generalizable because the students in the population change, the nature of the instruction changes, the nature of the exams that were given changes, the average age perhaps of the population changes. Why would that be generalizable? But I'm going to argue that qualitative research gives you results that are at least transferable, if not generalizable. And I'll try to give you an example of why I believe this. Trish Anderson a few years ago did a beautiful study where it was a case study. One of the cases involved a student that we gave the pseudonym Parker to. Parker was fascinating. He was a high A student in the freshman chemistry course for the majors. He got into organic. He barely got a C in the end of the first semester of organic. And before the second semester started, he was no longer a chemistry major. He was a political science major. Why am I going to use this? I'm going to argue that if I've got a Parker in my class, you've probably got the same kind of a PERC somewhere in your class as well. That if we really understand a handful of the students, typical students that are in our class and the problems that they bring to it, we can oftentimes do a much better job of talking about what it is that needs to be done in classrooms that are outside our own. Michael Quinn Patton's fourth edition is now out. He says, qualitative data describe, they capture, communicate someone else's experience of the world in his or her own words. And an important idea for us has been qualitative data tell a story. We found that we agree with his argument that qualitative research provides information about questions that revolve around better. Were better decisions made about how to study quantum mechanics, for example? Was there a better understanding of what is called in our business the arrow-pushing formalism that is used by organic chemists to describe the mechanisms of reactions? Well, here is the book. For many years, I asked colleagues who taught educational research classes, could you give me a reference that I could use with my graduate students that would provide them with detailed information that would allow them to decide what was the best theoretical framework for a particular study? And they would look at me and they would laugh and they would say, hell no. They just didn't say no. So we decided, okay, let's go out and do it ourselves. And we wrote a book on theoretical frameworks for basically qualitative research in chemistry or science education. There are 14 different chapters. They were written by ex-students of mine or colleagues from Purdue. This book sold for $25 when it was released. I went to Amazon about a year and a half ago. I found that they had a copy of it that was new that they listed for $3,487. I contacted them suggesting that that might have been an excessive price, to find that a couple weeks later it was only $200. I've gotten the copyright back from Prentice Hall, which by the way no longer exists. And so we're going to post this on our website. The thing that makes me proud about this particular book is that what we tried to do was describe where a theoretical framework came from. We tried to then cite some literature where it had been used, and then describe why it was appropriate for the particular study in which we used it. What makes me proud about this book is that several of my colleagues have noted that within 2 weeks of it arriving in their office, it got stolen. I'm going to talk about a handful of theoretical perspectives and show you how we used them. 30 years ago, I published a paper trying to define what the constructivist theory of knowledge meant in a language chemists could understand. We believe that constructivism, social constructivism, can be a very powerful theoretical framework for our work. So let's go back to how I described constructivism. I started the first paragraph and included the quote, "Teaching and learning are not synonymous. We can teach and teach well without having the students learn." And I've tried to capture the barrier to communication using a painting by one of my favorite artists, René Magritte. This is called Les Amants. If you don't know French, that's the lovers. There is a barrier to communication between students and their instructor, and vice versa, between husbands and wives, parents and children, employers and employees, and we've got an understanding of that barrier. I defined the constructivist theory in a 9-word phrase. Knowledge is constructed in the mind of the learner. I have never encountered a chemist who is unwilling to say that could be right until I tell them what the implications are. It's a very useful theoretical framework when what you're trying to understand is the process of meaning making, how individuals make sense of an experience. The example I can start with is Rob Ferguson's study of sophomore chemistry majors at the end of the organic chemistry course, where they were given a handful of problems such as this one, which is a borohydrate reduction of a ketone to a secondary alcohol, as I'm sure you all remember. And the idea of drawing a mechanism is to be able to use curved arrows, this arrow pushing formalism, to understand the flow of electrons, to understand the bonds that are broken, the bonds that are made in the course of a particular reaction, to understand what really happens at the molecular level. There are other ways in which constructivism it can be useful. We did a study that published in JRST not too long ago, where we were studying graduate students and young faculty, and in their ability to take spectra. The upper left hand corner is a Fourier transform proton NMR. The bottom right corner is the Fourier transform infrared spectrum. I've given you the molecular formula of the material. If you knew anything about NMR, you would probably know what you had to do. The people who were successful at this always did the same thing. They wrote down fragments of the molecular structure as they deduced them, and then they said, okay, I'll check my work against the other spectrum and then try to put it together. And the correct answer, of course, is the 2-ethoxy, or if you will, the ortho-ethoxybenzaldehyde. And the only way you really got credit for being right is if you actually got the correct isomer of this. But our goal is understanding how people make meaning of the spectrum. I want to talk about a theoretical perspective that I've found very useful, hermeneutics. The way in which we think about it today is providing a voice to individuals and groups who are oftentimes ignored. And to give you an example of what hermeneutics could mean in your life, I want to ask you to participate in a simple experiment. I want to ask you to raise your hand if you have ever done the following. How many of you have ever asked the students who were enrolled in a course to help you choose the textbook? Wow. It's got to be a dozen. That's amazing. Far better than chemists.
That's a dot, obviously.
But we have more textbooks to choose from. The problem here is that students have a voice that is usually ignored. Let me give you an example of a place where we use this within our own department. We have a course, 224, that deals with analytical chemistry techniques for people who are not chemistry majors. The students in this course are going to graduate and be analysts. They're going to use the topic of the course. In spite of that, what we found was that this is the most hated course in my department. And you have to understand that the courses against which it is being rated include things like a course on thermodynamics and, of course, the course on quantum mechanics. We went into it because it was hated. And we went in and we asked a simple question. Is anybody willing to talk to us about the problems with this course? And what was very interesting was that every single student enrolled in the course, there were over 200, volunteered to be interviewed. We didn't interview them all, but we interviewed a bunch of them. We got some really great suggestions, gave them to the instructor, who said, I can do that. I can do that. By the way, one of the ideas behind this course is that it was worth 12,000 points. I have no idea where 12,000 came from. But I do know I met a physics educator at an institution that will not be named, who pointed out that his course was worth 1,000,000 points. And he said he does that because no student has yet been willing to walk into his office and ask for an extra credit of 50,000 points for getting the question partially right. Joe Shane, who wrote about hermeneutics for our book, wrote about it because he had used it successfully in a study. We basically asked, what are high school teachers' beliefs about the intended and actual impacts of standards-based reform? And one of the things that I think is important from this particular study, and I'm going to come back to it, is the idea that there were not an infinite number of possibilities. Our teachers divided themselves into pretty much 3 different kinds of categories. Some overlap, of course. Let me take a look at a couple of theoretical perspectives that are somewhat related, but different. One of them is called phenomenology, and the idea behind phenomenology is that what you're trying to do is get what is the essence of an experience shared by everyone who goes through the experience. And one of the examples that is used by proponents of this philosophical technique is the common fundamental essence of being a father. So I ask this question. Is there indeed a common essence of this experience that is shared by all fathers? And the answer, I hope, is easy. If you read the newspaper, if you watch TV, you find that the answer is perhaps not. That perhaps not everyone goes through this particular experience, coming out with the essence of the beauty of being a parent. So we need an alternative, and we've used this one very often. It's called phenomenography. It's about 20 years old, a little less. The idea behind it is it's a framework for looking at differences in the way people experience what on the outside looks like the same phenomenon. So I'm going to ask a question related to our first study on phenomenography. And I'm going to say, let's assume that you were going to build a workshop for your students, a first semester physics course, to help them understand how they should study physics. What would be the first thing that you should do? And the answer, I hope, is that you understand that you would do something like what we did. We went out and we looked at students who had been successful, A's or B's in the first semester, who were enrolled in the second semester general chemistry course, and we started by asking them, how do you study? Because until we knew what it is that they ended up doing, how could we tell them what would be a good way of proceeding? How could we convince them to change? And we found again that they were essentially 3 groups into which people tended to divide themselves. Another example of a phenomenography study that was done by Shannon Daly, working with Robin Adams and myself from engineering education. And it was based on an experience I had when I first became a faculty member in engineering. I would be talking to engineers, and they would say the difference between engineering and science is engineers do design. And I looked at them and I said, you're crazy. You do design, we do design. I said, what is organic synthesis? If nothing, it is a design experience. And then I said, I know something about physics. You will sometimes encounter a cousin of mine's named Stephen Bodner when you read things like science, because he's oftentimes asked to comment on why the Lawrence Berkeley laser fusion experiment is not as successful as they anticipated it would be. And he's chosen because he had provided an alternative model that he said should have been followed. I know something about the practice of doing physics. And I'm sorry, anybody who's looked at the Large Hadron Collider has to assume that physicists do design as well. So what we did there is we asked this question, are there any similarities and differences between the definition of design across disciplines? And we looked at 14 different disciplines. We looked at experts in the field, from choreography through organic synthesis over towards engineering, and we found, using phenomenography, that there were ways in which we could group these kinds of experiences. I want to talk about critical theory because it's extremely important in my own work. Idea behind critical theory, overcoming uneven balance of power. We talk about achieving social justice. We talk about emancipatory knowledge. And when I talk to chemists and their eyes glaze when I use emancipatory knowledge, I said, okay, let me try to give you an example. Do you remember when you first learned how to ride a bicycle? Or you first got a driver's license? Or you got your own car? The ability to ride the bicycle, the ability to drive, is knowledge. But it's emancipatory knowledge, because for the first time in your life, when the parental unit asks, where are you going? You can answer out. So I want to return to the study Provi Mayo did for us on blind students and the kinds of structures of molecules that they draw. This is a structure that was drawn by one of our blind students using what's called a thermal pen. The thermal pen gives you a black line, but it also is hot. And when you use it on thermal paper, or sometimes called swell paper, wherever the thermal pen touched, the surface rises up, so that the blind individual can touch the drawing when they're done and process it using what's called haptic processing. Okay, so this is a drawing that was done by one of our blind students, and I'm going to assume that there's no one in this room who didn't once have general chemistry. I'm also going to assume that I may be the only one in the room who still has it. This is a simple structure. What is it? Is it a tetrahedron?
Methane.
And the answer is no. Methane has something in the middle that's bound to the things on the outside. So this doesn't make it. It looks like a tetrahedron, but it isn't. The individual was drawing a trigonal bipyramid. Every sighted person we've ever looked at draws us the trigonal bipyramid pretty much the way I've seen it, shown it here, with a perspective that goes like this, from the eyes out to the object. And I'm here to tell you that we've never encountered a blind student who draws from the same perspective. They tend to draw from a perspective from above. And so what you see is in the center, the atom that's on the top. You see their attempt to indicate that there's something happening with three atoms that are below it. There is a small dot that you may not notice, which was the central atom. And of course, the fifth atom is hidden beneath the diagram. The phenomenon is, in the absence of our doing this kind of study, we wouldn't have been able to explain why, when we brailled diagrams for students who were blind, they decided that they were worthless. We now understand what the problem is. And our idea is out of critical theory. It is this notion of emancipatory knowledge, social justice, being able for students with disabilities to pursue a STEM career. Not necessarily to become chemists, but to basically go into one of the many fields for which at least 1 year of chemistry or perhaps 2 years of chemistry are required. We've solved a lot of the problems associated with the general chemistry course. I'm working on the much more difficult task now of figuring out ways of helping them with organic chemistry.
We're actually close to time.
We're close to time. We got 6 more minutes and there's no time for questions. No, I'm sorry. I want to talk a little bit about the second half of Patton's book's titled Qualitative Research and Evaluation. One of the things that I found among chemists is there's an enormous amount of misconception about the use of 2 words, assessment and evaluation. In much the same way as René Magritte entitled this particular painting, The Treachery of Images, and said in French, this is not a pipe. He's right, it's not a pipe. Assessment is not evaluation, evaluation is not assessment. These terms are not synonyms. So we always have to remind chemists about the fact that you can assess students. They're assessed because it comes from a French term meaning to tax. You assess students, and you can use this as one aspect of program evaluation. The problem with program evaluation when it's designed by people who don't understand is that they start to go in with this notion, well, whatever we're doing is either going to be good for the students or it's going to be bad for the students. And the better your understanding of what the data really tell you are, is that effects of changes in instruction are bipolar. Some students benefit from change, others do not. Active learning has been advocated for use in physics. I've been on the program with Eric Mazur. I understand what he's arguing. I can appreciate it. I can support it. I can tell you that if my cousin, Stephen Bodner, had been involved in an active learning class, let's put it this way, he would not have benefited. It's not necessarily good for everybody. The problem that people have is that when they start to do evaluation, they forget to ask the Latin question, cui bono? Who is it who is benefiting? I want to conclude by giving you a model that I've been working on for a few years. We entitled it Overcoming the Sports Mentality Approach to Evaluation. We note that when you talk to chemists and you ask them what would they do to evaluate a change in instruction, they always come back with the same model. Let's compare students in an experimental classroom with students in the control group. There's nothing wrong with that. We've used it. But I'm going to argue again, there's nothing particularly right about it. And I'm going to use the metaphor of Billy Crystal, the comedian. He talked about growing up with his grandfather. And one day he came in and he asked his grandfather, who was watching basketball, what's the score? His grandfather said, well, it's 88-86. And so Billy Crystal asked his grandfather, who's winning? And his grandfather looked at him and says, 88. How big of a difference do you need? The other one is an interesting philosophical question. If you do this, you are assuming that an experimental technique that you've never used before, that you're using perhaps for the very first time, will become better in the first time out of the box than the technique that you have been evolving for the last 10, 20, 50 years. That's a hell of a standard to hold something to. I'm not saying don't look for changes in performance, but what I'm saying is that sometimes what you really ought to be asking is this. Sometimes our goal is just simply to improve student attitude towards a course. Neither you nor I, when we teach introductory courses, have very many volunteers. Very few people come to Purdue and say, I don't care what else you put me in, please put me in the freshman chemistry course. I've had 50,000 students, I know this full well. If I can improve their attitude during the course, I've improved the course. I want to talk about retention. These things, this is much more difficult to measure. And I'm not talking about retaining students. God knows we retain them far too long. Best evidence for that is the U.S. Department of Education requires that your institution report 6-year graduation rates. If that's not an example of retention, I don't know what is. Graduate students are not there for 6 years, they're there for 10 years. There was an article in the Chronicle of Higher Education a couple of years ago asking whether 10 years was a sufficiently long enough period of time for doctorates in the humanities, or whether we ought to be looking at 12 years. I'm not talking about that kind of retention. I'm talking about the fact that what we really ought to be asking ourselves is to what extent do students retain the information so that they can apply it the next time you come around. How do we overcome what we call the vaccination theory of education, student aversion? I had that once, I'll never have to worry about it again. Faculty leadership, we taught that to them when they were freshmen. There's no reason why we would have to revisit it now in the sophomore year. The state version, they had their course at the Community College of Abysmal Standards, which by the way is never in your state, it's always in a neighboring state. And now that they've gone to Berkeley, there's no reason for them to take the course again. How do we measure whether or not students are retaining what we want? And of course, transfer. There are people in physics who have been looking at transfer, more near transfer. I'm more interested in far transfer. The argument that I'm going to make is that the students are in your course, primarily introductory courses, because it's required. It's required because it's a prerequisite. It's a prerequisite because someone believes that that information is useful. Is it? And then finally, I want to give you the last one that we have been focusing on for quite some time. And that is, one of my goals is to help students begin to think the way a chemist would think, not the way a student would think. Thank you very much for your invitation. 1:15 by my watch. Anyways, there's never any time for questions. Sometimes there are.
I would actually suggest that the parallel session organizers maybe go upstairs and start getting ready, and then we have one question. I will allow one question, so we don't get really far behind. Anybody have that one question? Yes, sorry.
Mine was more of a comment, and I was going to make it privately, but then in the spirit of what we were looking at APT, I thought maybe some people didn't think of this, and maybe it might be worth everyone hearing. Which is to say, I loved your talk, and thank you. That was wonderful synthesis. But I would point out to you, in the spirit of the fact that you value critical theory, that when you define phenomenology, you provided an example of what does it mean to be a father, and what are the common elements there. And I wondered if you had thought about who you are in asking that question, and who your audience is in also pondering that question. Because there are quite a number of us who are not fathers and perhaps never will be. And therefore our access to that space is a little different. Another question you could easily have asked is, what does it mean to be a student? Because I would bet that all of us have access to that space. And I am, of course, beautiful, and I know you're aware of this, but it occurred to me that some of your listeners might not have heard the question in the same way.
I use the example of fathers because that's the example that von Manning uses when he defines this technique. There is a similar argument for mothers, for parents, where we wouldn't worry about the assessment of which sex it would be, just simply being a parent. When we apply this, however, we are always applying it within the environment of students. We are always asking, how do students differ in the way they go through a particular experience? The argument I'm trying to make is just that we should not assume that there's only one way of going through the experience, that the same experience can be experienced in different ways. And the people who wrote about phenomenology basically said that there's always a limited number of these options. It's not a huge number. For us, it's usually been about 3. So I really do understand. I use that particular example because it was a quote.
I think maybe somebody should have asked him those questions.
I have. The second edition hasn't appeared yet.
Let's thank you guys again. We're going to go to, yes, thank you.